Okay, this is Physics 1C for October 27th. And here's the topics we're talking about tonight. We're going to finish discussing Ampere's law and magnetism. I'm going to refresh what Ampere's law was, and then we'll do a problem to kind of cement that review. And then we'll talk about different types of magnetism and kind of like where magnetism comes from. So that's part of what we're talking about tonight. And then we're going to get into a new topic, which I think is like chapter 30 or something in your book, which is electromagnetic induction as governed by Faraday's law. We'll learn what Faraday's law is. That's going to be the last of Maxwell's equations, actually. And so we're going to learn about how it is that a moving magnet can induce a current into a wire, and how electrical power is generated and all these kind of stuff. But we're going to start off with this Ampere's law thing. So let's review what Ampere's law states. Okay, so last time we talked about Ampere's law, and Ampere's law describes how a current-carrying wire can produce magnetism. And the way we can think about it is that if I have some wire that carries current, and we call that current I, what we showed last time over the last few weeks is that around this wire, there's going to be a magnetic field that's generated, and it's going to have a nature such that if you point your thumb along the wire, then you wrap your fingers in the direction of the way your fingers of your right hand would wrap, then you're going to produce this circular magnetic field around this. And these circular magnetic field lines, they kind of go around it. Whoops, not like that. This way and this way. And what we can do is we can think of this wire right here as if the current is flowing kind of into the page, because it makes it a little bit easier to draw these things. And so if we imagine that this wire carries a current I that flows into the page like this, and we surround it with a circular loop, like that. And we'll give it a different color too. I'll move it a little bit. Call it red or something. That if we do an operation called what's called a line integral around this loop in a certain direction. In this case, what we're going to do is we're going to go around a path like this. Then what Faraday's law states is that if we integrate the magnetic fields dot products with the path, and your book likes to use the symbol dl, that this is equal to mu naught, which is the magnetic constant in space, in free space, multiplied by the current that is enclosed. Really what this means is by the loop, the current that kind of flows through the loop. So in this case, there's a current that's flowing into the page as represented by that X there. That means current flowing into the page. And this tells us how to calculate the magnetic fields. So what we use this to do is we use this to find magnetic field right here. In this case, what happens is that, just as it shows in this picture right here, it turns out that at any point along this loop, the magnetic fields... Here, I wanted to kind of use the same color. I'm going to use this one. At any point along this loop, the magnetic field lines are going to be tangent to the loop like this. So at that point, they would point that way. The magnetic field here would point this way. And really, the path that we've chosen here is actually kind of identical to the direction of the magnetic field at any given point. That's helpful because the path direction is given by this vector dl right here. At any element of the path, this dl just represents the direction of the path at that point. And so if you come down to like this point right here, then the magnetic fields and the dl vector point in the same direction. And this tells us how to find the magnetic field. And by using this, we can prove that, maybe we just do it again because it's a really short proof. If b and dl point in the same direction, then this is just going to become b times dl. But in addition, the magnetic field is likely to be constant all along this path because you're the same distance away. In fact, if we call that distance r right there, then this magnetic field should be constant with respect to every point on the path. So the integral itself can be reduced down to just b times the line integral of dl, and that's equal to mu naught times the current enclosed. I'm just going to say that current is I in this case. And then this path integral just says to integrate the path, which is going to give us the length of that path, And since it's a circle, the length of the path is 2 pi times r. So this ends up being v times 2 pi r. And this allows us to get a result for the magnetic field of a long current carrying wire, which is that the magnetic field is equal to mu naught times the current divided by 2 pi times the radius. We used this to solve a few problems last time. But Faraday's Ampere's law, this is, I should have written this down, this is Ampere's law, tells us how to do that. And what we'd like to do is to apply this to a slightly more complicated situation right here. That's what we're going to do. Okay, any questions about Ampere's law? No? Okay. So let's see if we can use it to solve this problem here. Why can't I select it? Oh, I know why. I need to be on this one maybe. And I'll scroll down just a little bit. Okay, so in this problem, what we have is a cylindrical conductor. I'll make this bigger. This has to be kind of hard to see. Can you all read the words? Is that large enough? Okay. All right, we're going to find the field of a long cylindrical conductor. This is a problem that comes up in your next lab annual homework, I believe. Not this exact problem, but something like this. So you have a cylindrical conductor with a radius r, and it carries a current I. The current is uniformly distributed over the cross-sectional area of the conductor, so it's a uniform current density, you might say. We want to find the magnetic field as a function of the distance r from the conductor for both points inside and outside of the conductor. Okay? And here's their picture right here. So you've got this golden, maybe it's made of copper or something, cylindrical conductor. There's current flowing from the top right to the bottom left. So the current's flowing in that direction there. And we'd like to use Ampere's law to create some paths. These paths that are created here are called Amperion loops, kind of like Gaussian surface, but it's an Amperion loop. And it's a path around the conductor. And we'd like to be able to describe the magnetic field inside and outside. Outside, it's going to be the same as what we found before. Inside, it's going to be slightly different. Okay? So let's take a look at this path that's drawn inside of our conductor right here. Okay? And let's draw it in the following way. The current is flowing from left to right. So let's say that we're looking at it from this end right here. If we're looking at it from this direction here, it's going to look like the current is kind of coming towards us. So what we'll do is we'll draw a circle, and let's see if we can make it similar color to what they have in the picture. Can I fill it in? Ooh, I don't know how to do this on this program. That's okay though. What I want to fill this in with is just these currents. And they're using purple, we'll use purple too. And I'm going to say that now we have this current that's coming out towards us. But what I'm going to say is that that current kind of has a density. And I'm just going to indicate that with these little dots to represent how the current is flowing. Right here. There's current flowing in this direction. You can think of it as like little tiny pipes that are carrying water or something. But in this case, they're carrying not water, but little charges that are flowing. Okay, so those just represent the current that's coming out right there. And all in total, all of those currents, they add up to a current I. But that current is uniformly distributed. So any given part is going to have the same amount of current inside of that. So this current is, as they say, uniformly distributed over the cross-sectional area. Okay, so we can think of it as like little pipes of current, and we're going to make a path within these, and the path that we're going to choose inside of them is going to also be a circle. So we'll just make a smaller circle inside of this one. In fact, maybe I make this one a little bit bigger. Oops. That way this won't look so bad. So now we'll put this one inside here. Maybe make it a little bigger too. I might make it black as well. black worse? I don't know. So that's going to be our path, and this is going to be our conductor. So on our path, we're going to make our path flow in this direction here. That's going to be our path direction, okay? So that black line right there represents the path that we're going to take for our Amperion loop. And we're going to give it a radius. So does it say, okay, the external radius of this object is capital R, and we're going to use a little r for this one here. So we'll draw just a radius here coming out from the center, and we'll say it has a radius of little r. And then the total radius out to the outer part is just going to be big R. Like that there. Okay. All right, so now what we're going to do is we're going to apply Ampere's law. So Ampere's law says, again, we need to do a path integral of b dot dl, and that this should be equal to mu naught multiplied by the current enclosed. Our goal here, again, is to solve for the magnetic field. That's what we want to find. We're trying to find the magnetic field as a function of the distance r from the conductor. So let's go ahead and handle that. I would argue that, similar to the previous problem that we had done, that the direction of this magnetic field here, at any point, it should be tangent to our wire, and that it should be constant, not tangent to our wire, tangent to the path that we've chosen here, and that this magnetic field should be the same at all points along the path. Individually, each of these path elements are going to point also parallel. Let's use a different color so it stands out a little better. Just like light green or something. So for the path, we're going to say that the path also points in the same direction as the magnetic field. The path is dl, so that's this right here, the dl. And any point where we have a magnetic field, the magnetic field and the path are going to line up. If they line up, that tells us that we can remove the dot product here because the angle between the two vectors is 0. And since the magnetic field is constant, we can pull that out again. So the left-hand side of our equation is going to be very similar to what happened in the previous problem. We're just integrating along the closed path. That's what the circle here represents. We're doing a closed path, the line dl, and that's going to end up being the kind of arc length of this. And since it's a circle with radius r, the arc length is going to be 2 pi times the radius. Does anyone have any questions about the left side of this? You'll notice that it's very similar to what we did in the last problem. Okay, the right side of this is what's a little more tricky, and will also be a little trickier in your problem too. So we need to be able to figure out what this quantity is. How much current is actually going to be enclosed, within this region right here, basically. How much current do we enclose with our path? We obviously don't enclose the entire current I. We enclose some fraction of it, right? How could we describe the fraction of current that we actually have there? What fraction of the total current that flows through this system is within this region right here? R minus R over R. So you're thinking it's going to be something that's related to the ratio of their circumferences. Notice what it says in the problem here. It says the current is uniformly distributed over the cross-sectional area of the conductor. So Post is also saying something like R over R. That would mean it would be a function of their circumferences. What does it mean? The current is uniformly distributed over the area. What that tells me is that if I was to take the current and I was to divide by, let's say, the total area, so we say that this thing has an area A on the end, this is what's constant. Oops, not cosine, constant. What is I over A? It's density, right? What's the symbol we use for this? Do you guys remember? Current divided by area. Sigma was the charge density, or conductivity, I think also is sigma. This had a different name. It's J. Yeah, it's J. It's actually a vector too. And the vector kind of points in the same direction the current goes. Yeah, we call that the current density. So this is the thing that's constant, right? This is the thing that's constant. So if I have a section that has a smaller area right here, like this is clearly a smaller area, right? Then if I just take the area of that little area that I was scratching through there, and I multiply by the current per area, right? Then that should give me, you know, the amount of current that's in here. Did that make any sense? I'll write it down. I would argue that that current that's enclosed right here should be equal to the area inside of my Amperion loop here, which is pi r squared, times the current density. And the current density is I over A, where A is related to the radius of this piece, which is big R. So it's I over pi times big R squared. Does that make sense? So it ends up being not R over R, but R squared over R, R squared. That's the ratio that you want here. Does anyone have any questions? So we get this relationship, cancel the pi's, and now we can divide the 2 pi r to the right-hand side, and I think this is what we get for our final answer. The magnetic field is going to be mu naught multiplied by the current I. On the bottom, we're going to have a 2 pi and a big R squared, which are constants. And then the one thing that's going to vary here is going to be little r, so we'll put that on the outside. So it's basically this big thing here multiplied by little r. That would be the magnetic field for the region where little r is less than the outside radius. This gives us the magnetic field inside. What would that look like if I plotted it? Assuming that all the things in parentheses here are, yeah, linear, right? Yeah, absolutely. If we plot the magnetic fields as a function of the radius, and we come up to a point capital R, then we would just have a straight line. And right at that point where, if you look at what happens here, I need to make this axis just a little bigger here, I guess. No, what are you doing? Here we go. So right at this point right here, the magnetic field at that point is where little r is equal to big R, and at that point the magnetic field is going to be equal to mu naught times I divided by 2 pi r, right, it's big R now. And that happens to be the magnetic field that we got in the previous problem when you just have a regular line. And then as you go outwards, if you want to write what the magnetic field is once we get in this region right here, well then at that point, the current enclosed is just going to be I. Big R will go into this piece right here. And so for the region where you get outside of the wire, your answer is just going to be 2 pi divided by R. And that's in the region where little r is greater than R. And they match at the boundary. And this is just magnitude. But the direction is, you can kind of see the direction here. Okay. Does anyone have any questions? I'm going to solve this again to give you a hint, but go ahead, Miars. So once we get to the position where, you know what I could do? So let's take the same derivation we just did, okay? And let's think about what happens when we make our Amperion loop here outside. In that situation, what happens is I've got my my loop right here that carries my current. Except at this point, I know that the total current, is now I. Yeah, there's no J basically, or it's yeah. Now the total current is I, and when I draw my Amperion loop, oh no, I hate the way this thing works. Okay, so now when I draw my Amperion loop here, I'm just gonna have to do this with the mouse. What's it doing? Did it switch back? Yeah, it's doing this. I gotta figure out how this thing works. Okay. Oops. We want to squish it, don't we? Want it to look more like a circle. There we go. So now when I do my Amperion loop, let's see. So the current is going out. I don't know if you figured this out yet. If the current's coming out, I need to make my loop direction, or the path, it has to go counterclockwise. Can everyone see why? This is a little bit important. It's only a little bit important. If you mess this up, you'll be off by a minus sign. It's not a big deal. If you point the thumbs of your right hand coming out of the board, it's almost like put your palm on your screen with your right hand, point your thumb in the direction of the current, which is out, then you curl your fingers in the direction of the way you want to do the path. And the reason for that is because that's how we know the direction the magnetic field goes. Okay, so let's repeat the problem again. So now on the left-hand side, nothing changes, right? Because now we define this radius to be r, all the way out here. And we define this radius to be big R. So the radius for our path is what shows up here. This is the path side, right? The radius for that path is still r. And we can still make all the same arguments. Magnetic field is parallel to the path. And yeah, all the same stuff over here. Now on the right-hand side, what happens is that I enclosed, really what happens is that this is the only thing that's going to change. Because now it's like, well, the total current enclosed is really I. But if you want to argue it from the exact same way we did before, it's really just pi times, oops, didn't make that quite low enough, did I? It's really pi times r squared like this. And then those two just cancel. And these are equal. So you end up getting b equal to mu naught times I over this piece. Okay. Any questions? I'm going to show you one more way to do it too, to help you out a little bit with the lab mail problem that's a little trickier. Any questions at all? So how we do this? I want to move on because the other stuff we're talking about tonight is quite interesting. But the next part is helpful to the lab manual problem you have. Why won't you let me move right? Okay, so let's redo. Oh, I've removed it all up here, haven't I? Well, that's okay. It's still there if you rewind the video. So what's another way we could have done this process here? Here's the other way we can do it. There is another version of Ampere's law. Okay, we're gonna get the same answer here, so maybe we can leave that there. There's another version of Ampere's law where you write it like this. So on the right-hand side, you still have mu naught, but instead of writing I enclosed, what you write is, and I'm going to do this to help some people out, because I was noticing, you do a surface integral of the current density dot products with dA. So I want to show you how you get the same answer both ways, but this is kind of your more general version of Ampere's law, basically. You change I enclosed to this piece right here. Now, it turns out current density is going to point in the direction of current. So the current density is actually, see, J is that way. And the area vector would be the area vector associated with, well, the path encloses a surface, right? There's a surface right here inside of our path, right? So that's what our area vector is going to be. And, it's basically going to be pointing also, God, it's so hard to draw this in here with all these other little things, but your dA is out of the page too. So you have j dot dA. They go in the same direction, right? So again, it's going to be j dA like this. Okay. So our right-hand side of our equation now, let me erase this little piece that I broke up here. the right-hand side of our equation now is going to be the integral of, we're doing the surface integral of JdA. Now, J, what's J? It's the current density, and we already said it's a constant. It's a constant over the surface, right? It might not be in your homework, but it's a constant in this problem. So we can pull that out. So we end up just doing mu naught times the J times the surface area of this loop. Okay, the area of our loop now is what this represents. And what we could do is we could say, okay, well, what is the dA now? The dA is going to be kind of like, if you imagine breaking this object up into little rings, I would argue that the dA piece is going to be 2 pi r dr. And the idea would be that you'd be, I can't really draw on here, but you'd be breaking this object up into a bunch of little rings, and you'd be summing up all those rings together. So the dA becomes 2 pi r dr, and then when we integrate this, you get mu naught J, which was I divided by the area. The area was the area of our loop, which is pi r squared. But when we do our surface area here, what we're going to be doing is we're going to be integrating just from 0 to big R. And so the integral here is going to give us r squared over 2. So you'll get pi times big R squared. Kind of scrunched everything in here, but this reduces down to the same answer. Oh boy, I'm sure that was really confusing, and I apologize. I shouldn't have tried to scrunch it all in that area, actually. It's confusing enough as it is, but did you have any questions about that? It's okay if you don't. But if you have questions, please don't hesitate to ask, because you will have to do this on your homework. On your homework, the big difference is that your J is going to be like a function of R, you know? This J is going to be a function of R, so you won't be able to pull it out. But at the end of the day, the problem's not going to be that much harder, because you're just going to be, you're going to have this is going to be the same. The dA is going to be the same, okay? But your J will be like a constant times R cubed or something, right? So here, when you do your integral, it'll be r to the 4th, and then you'll get pi r to the 4th over 4. You know what I mean? And it'll be... Does that make sense? J is going to be your function. That's going to be what's going to be a little bit different in the homework problem you have. I think you have more than one of these that uses Ampere's law like this. They're actually... I don't think they're that hard if you follow this method and you understand kind of like what this means. If you don't understand what this means, I understand. This is the same result, r less than r. All of this stuff here is the same result of the r less than r case. Yeah, r less than r still. We're still inside. And once we get outside, we do that. Yeah. This is still r less than r. Oh, did I flipped this. I flipped them. Oh, I'm so sorry. This, here, I'm going to put it in a different color so you can see what my errors were. Yeah, I see why you're confused, Keanu. That actually makes a lot of sense. Because this should have been, this should have been, okay. These two I got backwards. Here, let's fix it. Okay, so, I mean, the pi's were fine, but, so the thing I messed up was J, we said, was I over A, where A came all the way out to big R. So this should have been divided by pi times big R squared. Times our integral here should have gone up from 0 up to some, maybe r prime, like a dummy variable. So that when we do the integral, you get pi times r squared. Yeah, that's right. That's what I should have done. Thanks for catching that. Or asking a question that helped me to see it. All right, so what I'd like to move on to now, and I think we can finish this in the next 30 minutes or so, I'd like to talk about types of magnetism, and really I'd like to talk about kind of where magnetism comes from, okay? Now, I saw a good video this afternoon from this physics club thing that I've been involved with for a few years. We were talking about magnetism today, and this video is honestly like a pretty good description, a better description than I could possibly do, but I will set it up to say the following. y'all know about electrons, right? And you probably know that electrons have this property called spin, right? Is that right or wrong? Have you heard of electron spin before? You're saying yes? Okay. So what we've discussed up till now, in the last 3 weeks or so, because we had the exam, is the magnetism that comes from wires, right? The magnetism that comes from electrical currents. And what we now like to do is we'd like to connect that to the type of magnetism that we see in the real world. So yeah, maybe now you understand a little bit about how magnetism is generated by wires and electrical currents, but then you could ask the question, well, how do you get a permanent magnet, right? Oh, did I integrate it wrong still? The two right here gets rid of the 1/2. Yes, I skipped a step. Sorry. That 2. We're integrating 2 RDR, right? So yeah, good point. I'm glad you're watching out. So with magnetism, okay, materials. How do you get a magnet like the magnet on your fridge, or how do natural magnets occur? How do you have magnetism in the Earth, right? And what I would say is that ultimately, magnetism in materials basically arises from electrons. Because electrons have this property that they spin. An electron, we think that some of them might be spinning kind of like this, in which we might say that that's a spin that points upwards. Or they might have a spin that points in the opposite direction, right? If the electron happens to be spinning on an axis that would go back this way. We might call that spin down. But the idea that we have this little spinning electron means that we've kind of got this charge that's moving. Now, here's the part where I can't really say that this is like a current, right? You might think of something like, if I have an atom, let's say you take a hydrogen atom. Hydrogen atom is pretty simple, right? Hydrogen atom has 1 electron. And if I had an electron kind of going around like this, around a hydrogen atom, around a little orbit that's like a circle, then you'd say, okay, well, there's this charged particle and it's moving in a circle. That's like a current. Would you all agree? It's kind of like a current. Little electron going in a circle. That's kind of like a current, right? And we'd say that would be almost like a current flowing in the opposite direction, I this way, right? And then we'd say, well, according to what we've learned, that would produce a magnetic field this way. And really what we'd say is that there'd be kind of like, instead of saying a magnetic field, the more proper way to say it is that this atom itself would have some kind of magnetic moment that would point this way. Remember, magnetic moment was the current multiplied by the area of the loop, right? Now, imagine that I have a whole bunch of these molecules. If enough of them line up in the same direction with this magnetic moment, then you could get a permanent magnet. But hydrogen is not usually considered to be a magnetic thing, right? It's a gas, right? You don't think about gases being attracted to hydrogen, right? That's not something you learn about. It's not something that you probably experience either, although we're going to learn that maybe some gases do in certain forms. So really, the magnetism is going to come from certain materials. And it turns out that this magnetic moment associated with the orbit of the electron is really small compared to the magnetic moment that might be produced by the spinning of the electron. Now, why a spinning electron actually produces a magnetic moment? That's beyond the scope of this course. It's something you learn about in quantum mechanics. That this spinning electron actually has a magnetic moment, and it's a quantum mechanical phenomenon. Now, I don't know how much of that is discussed in 1D. It's more likely, if you want to learn more about that, you're going to need to kind of like read more on your own, like all that kind of stuff. But in general, it does produce a magnetic moment. The electron spinning in a certain direction is going to have a magnetic moment that's going to point one way, and I might be getting this wrong, but I think if the spin goes up, I think the magnetic moment also goes up. I could be getting that backwards, though. I'm not sure. And if the spin goes down, you could think of that as a magnetic moment going this way. And maybe the word magnetic moment just makes you queasy because you don't know what it means. What it really means is it's quite literally like we have a magnet associated. Saying a magnetic moment points down like this is like saying this guy acts like a bar magnet, where the north side of the magnet, maybe we use red for north, and maybe we use black for south, then this is the north side, this is the south side. When I say magnetic moment, that's all that I mean. Yeah, tendency for something to be magnetic or to respond in the presence of magnetic fields, to act like a compass, to point, right? So this is where I'm going to let the video take over, but the general idea that I want you to take away from the video you watch is this, right? Imagine that you have a piece of iron, and imagine that piece of iron is unmagnetized. Okay? If it's unmagnetized, what does that mean? Well, it means that within the atoms of the electrons, within the atoms of the iron, that there's basically going to be these randomly oriented, and I'm going to use an arrow here, just like I've done up here, to represent either spin up or spin down regions, okay? Maybe that everything is randomly oriented, okay? And I'm not going to completely do this properly, but we just have these randomly oriented magnetic spins, like this right here. So each one of these arrows represents a little magnet. This represents the north end, and this represents the south end, okay? So maybe they're all just randomly aligned, okay? But then suppose that you take this same piece of iron and you place it inside of a magnetic field by putting a magnet on one end or something like that. So let's do that. Let's say that we take a magnet, north end here, and the south end over here, and we put our little piece of iron on the end of it, like this right here. Well, all those electrons inside are going to tend to want to respond. And by having a magnetic field that points this way that's applied externally, on the inside, a lot of these things are going to start to line up. Okay? And what that's going to do is it's going to make this the north end of the bar and this the south end. Then all of a sudden you can pick up little paper clips and stuff with this. You know? They'll be attracted. Or little nails and stuff like that will be attracted. Right? And that's generally the idea, is that there's something about the electrons, okay? That you get enough of them and they start spinning all in the same direction, and all of a sudden you get a permanent magnet. Did that explanation make any sense? I'm just covering the basic details, and we're going to watch this video that I think does a better job of explaining what I said. And covering kind of more of the chemistry part of it too. Okay. Just think about that though, just for a moment, just like kind of take in what we're saying here. In this course, we started off with charges, right? Just little electrons. And then we said, make those electrons move. When they move, you get this dynamical thing called the magnetic field that happens, right? These moving charges and wires, they produce magnets, right? So it turns out that even in a piece of iron, a permanent magnet where you think that's what a magnet is, what's the magnet? Well, it's actually electrons. It's the electrons that do all the work for all this stuff. They produce the electric fields, they produce the magnetic fields, they make permanent magnets. It's all the electrons and the way that they respond, and the fact that there are so many of them that even a small change overall can produce this type of effect right here. So, anyone have any questions while I pull this up? I had all these other videos pulled up here and I lost. Let's see if I can find the other video real quick. Should be in my history because I watched it today. It's called... Wait, where did it go? That's weird. Okay, magnets. I think this is the one. Okay, we gotta let some videos, some ads play in the background. I'm not gonna subject you guys to the ads. All right, there we go. So okay, let me answer your question. It says unmagnetized means the net magnet. Yep, that's right, Miars. Unmagnetized means the net magnetic moments all add up to 0. It's almost like perfectly randomized, so there's no exactly. It's randomized. I don't know how many of you have taken or are currently taking 1B, but it's really about that. It's about the fact that these little atoms and the electrons within them, they're subject to a temperature, and that temperature makes them kind of fluctuate and jostle around and wiggle. Everything wiggles. You know, that's what happens on the tiniest scales. Everything's wiggling and moving and jiggling and bouncing off each other. And given enough time, yeah, they become a magnetism. You know what? Another thing I would like to mention here about this is something the video won't mention. If you take If you take a magnet, you stick it on a piece of iron, right? You can actually break the iron off right here. You can just take the piece of iron away. It'll still pick up things for a short amount of time, right? But given enough time, temperature will actually cause it to go back to this state up here. It'll eventually go back to the state of unmagnetization. And an even crazier thing is, you can literally take the bar and you can bang it on the table. I wish I could do this demo for you. It's a demo we have at the school. You can bang it on the table and you can make it lose its magnetism just by the vibrations of the atoms themselves. It's crazy. It's just absolutely crazy. So it goes to show you that it is a phenomenon that is definitely associated with order, right? It's an ordered phenomenon. And yeah, so okay, let's watch this video. I need to make it so you can hear the video too, so let me do that real quick. I think we're probably going to watch both of these videos back to back, because this will be naturally a way to go into the video about different types of magnetism. Let me know if you can't hear it. You can't? Thank you. Okay, change windows. This guy. Go live. Okay, give me a quick yes or no. Okay. Yes, that other video is actually really good that he's referencing. If you've studied special relativity, it's definitely worth watching. If you haven't, I don't know if it's interesting, but okay. Does anyone have any questions or comments about? Yeah, so you should watch this video that he's saying right here. I'll link you to it. Can I link it through the video? Well, this is gonna. There's a lot of. There's actually an explanation in your Physics 1C lab manual. I have to find out where it is. It's toward the end of the lab manual. Okay, yeah, you can look at Veritasium and just search for special relativity, and you'll probably find it. Yeah, does anyone have any questions? Any comments about what's going on here? Did that make sense? Did that help you to understand the idea? It's not as simple as I made it. It's not like just a bunch of little arrows, right? It's a lot of things coming together, a lot of order. It's all about order. You know, it's about these electrons line up, and then the pieces of the electrons line up. Yeah, it's really, really well done for a 6-minute video to explain all those complicated ideas. But I really like how your knowledge of chemistry kind of comes into play here, where you understand this idea that the shells get filled up, and when they fill up, the way that they fill up is like, you know, you can have in one shell you can have an up and a down electron, but if you have a shell where 2 of the electrons are going upwards, those 2 can kind of add up to give you this thing. So we're gonna look at another video, because the type of magnetism that he's discussing here is called ferromagnetism. He used that word, right? Ferromagnetism is the type of strong magnetism that we see in the world, but there are 2 other types of magnetism that exist as well. And we have some nice demos for this at the school, but there's a video here that I found about paramagnetism and diamagnetism. This is another type of magnetism that exists even in materials that don't happen to be one of those 4 that he mentioned there, you know, the iron, the cobalt, the nickel. Manganese, I think, was the other one, right? So, yeah, so we're going to watch this video. This is from UCLA, and it's about the other 2 types of magnetism. And then after this, we'll take a break. So if you do have any questions or anything, let me know. one thing I'm going to mention is, like, we actually have this demo. Maybe have any of you seen it? I don't know. This demo right here that he keeps doing. We have exactly the same demo at El Camino. It's like the same substances too. It's like cupric sulfate. There's a water one, and then there's like a few of these other ones too. And yeah, I have to say, the first time that I did this demo, or had the demo showed to me, I should say, I was really surprised, because I think when I was studying physics, this topic wasn't brought up. So I was like, really? These things, they can actually be attracted? Like, the idea that water can be attracted to a magnet. Did any of you know that? That water can be attracted to a magnet? Yeah, I didn't either. I thought I found it really surprising. Yeah, so there we go. That is, yeah, graphite is really surprising too. I mean, it's just pencil lead, right? I wonder if it's that particular type of graphite. So did you notice how small it was though, Ash? It would have to be a very slow drip of water, probably. Yeah, it's a really small effect. It's nowhere near as big as the effect. Well, I think we saw that. Yeah, gravity probably would win out. I think we saw the effect that you're describing with a charged rod, right? A charged rod, I believe I showed you, one of the videos I showed you involved a charged rod with water flowing near it, and it basically deflected the water. Do you remember that? Probably not. Been a long semester, but toward the beginning of the semester, that's one of the things that I believe that we showed you. And it's definitely, it's a demo that you can kind of probably do yourself with a comb. So if you want to deflect some water, Ash, I would say take a plastic comb and run it through your hair, like through your dog's hair or something, and get it really charged up and bring it near to a very kind of like thin stream of water, like on the lowest setting that you possibly can on the faucet, and it should be able to be deflected a little bit by the comb. Give that a shot. You're gonna have to get it really charged up, so you make sure you can dry your hair off, like make sure your hair is really dry, and make sure the comb is really dry too. And then make sure that, like, when you're combing through your hair, that you hear crackles. Those little crackles indicate that you're building up a charge. And it won't stay very long either. So, okay, it's 7 p.m. So this is as good a place as any to take our break. And then when we come back, we'll just jump straight into talking about electromagnetic induction, and we'll do that for the rest of the class. So let's take a break until what is it going to be, like 7:11?